Jill, please.
Okay, it's a great pleasure now for me to introduce an old friend of mine, Professor Richard Didier, whom I've known for about 30 years. He is now the head of the architectural and design science and the director of the Indoor Environmental Quality Laboratory at the University of Sidney. Richard is going to broaden our vocabulary. He's going to talk about alliesthesia. I know what it is, and I've known for about 1 hour now. I asked him before the presentation, but just wait a few minutes, and you sure will know what it is. So the title of the presentation is Thermic Alliesthesia, Better Than Thermal Neutrality. Richard, please.
Thank you, Geo, for that introduction. But you do know what alliesthesia is, because I told you just before the presentation. This is a talk about the phenomenology of thermal comfort, how we actually sense the thermal environment around us. And I think you'll see quite quickly that it's very, very closely related to Professor Ju's presentation, the first one in this session. I've got one of my PhD students listed here as one of the co-authors of this presentation, Thomas Parkinson, and his project is doing some experimental work on alliesthesia, and so I've borrowed some snippets of his latest findings to flesh out the topic. So, what's happening? It's not responding. To go forward. Okay. So an outline of this lecture in the next 30 minutes. I'll spend the first part of it having a look back over the history of thermal comfort and how air conditioning has been applied to that problem of thermal comfort, and the trend over the last 100 years has been essentially a gradual tightening of temperature control inside buildings, on the assumption that that's what people want, that that's preferable, that thermal variation is actually an undesirable aspect of indoor climate, and that air conditioning is the strategy for removing variance from our thermal experience. So then we'll have a look at the way that engineers have gone about that task of removing thermal sensation from our environments and creating neutral thermal climates inside buildings, neutral being devoid of any thermal sensation whatsoever. Then I'll introduce this concept of alliesthesia, which is an old concept, goes back to the 70s. It's borrowed from the physiological sciences. Well, not borrowed, but it was developed initially in the physiological sciences. Professor Kuno from Nagoya University has, I think, one of the first to introduce it to the thermal sensation, thermal comfort world. And I think it has a bearing on many of the issues that Professor Ju was talking about in her presentation this morning, and that Professor Ahrens will be talking about after I finish this presentation. So I'll finish the lecture with a discussion of some of the experiments that we're doing on this topic of alliesthesia, just briefly. So what's I guess the elephant in the room when we're talking about temperature control and tight temperature control is the energy implications. So I've got a slide here from our friends at Berkeley that illustrate the energy savings that can be achieved by widening the deadband, by loosening temperature control inside buildings. And using a baseline of 2 degrees, as 2 Kelvin as the width of the deadband, expanding that out to, on the cool side or on the warm side, to 3 or 4 degrees can achieve very substantial HVAC energy savings. So this data that we're looking at here were the results of some energy simulation studies in a reference office building in various climate zones around the United States. So, as I was saying, the thermal comfort standards, the way air conditioning is applied, has basically been to narrow that deadband through the decades of the last century. And as technology has improved, the tightness of control has also contracted. And now we actually get to the point where we're rating buildings, we're assessing buildings, giving them brownie points in various rating schemes in terms of their imperceptibility, how successful the HVAC system has been at removing any thermal sensation. So let's have a quick look at the standard or official definition of thermal comfort as it appears in ASHRAE's documentation in the standard and the handbook. It's that condition of mind that expresses satisfaction with the thermal environment. Satisfaction. So when we come to actually operationalize that definition, to put it to work, you'll notice that we use a different lexicon. We've got the rating scale that we use for thermal sensation is, it's been referred to several times this morning already. It's a 7-point rating scale, but the midpoint has no reference to satisfaction at all. The optimum score on this 7-point rating scale, as it's used by engineers, is neutral. In effect, it's a subtractive definition of thermal comfort. It's the removal of warmth or coolth from our thermal experience. And it's important to note that there's no reference to affect, no reference to liking or disliking or satisfaction. It's just neutral. So the way thermal comfort is described in ASHRAE's documentation in the standards and the handbooks relates back to some pioneering work by Fanger, who wrote the Bible, if you like, on thermal comfort back in the 1970s. And Fanger ingeniously solved the heat balance equation for the human body by overlaying empirically derived comfort temperatures at different metabolic rates, and also overlaying the skin temperature that corresponded with thermal comfort at these different metabolic rates, but also the amount of evaporative heat loss at different metabolic rates. So putting those three equations together came up with what we now refer to as the comfort equation, which can be solved very simply by means of readily available software tools by inputting 6 basic comfort parameters. 4 environmental parameters, including air temperature, mean radiant temperature, air speed, and humidity, and then 2 personal parameters, metabolic rate and clothing insulation values. So it's a very, very simple, very useful way to present the problem, and I guess the success, if you like, of this technique owes largely to the fact that it is so readily accessible and so easy to apply. Now, from that basic thermal comfort equation came 2 thermal comfort indices that are very widely used. One refers to the predicted mean vote scale. Predicted mean vote is simply a solution of that equation so that it predicts the average thermal sensation on that 7-point scale of a large group of people exposed to the conditions that you've described by those 6 parameters, the 4 environmental and the two personal. So in this example here, the predicted mean vote is plus 1.8. So that's the PMV index. The second index, very interesting, and very useful as well from an engineer's practical point of view, is the predicted percentage dissatisfied, or PPD. And PPD is taking account of the fact that we're not all the same, that actually our thermal comfort responses to a given exposure are varied from one individual to the next, but if you had a large group of people exposed to the same conditions, they would describe something like a normal curve, a normal distribution. And so PPD tells us how much, or what percentage of that normal distribution is sitting in the tails, in the extremes of the normal curve, outside the central 3 votes on the 7-point scale. And as you can see in this graph here, the PPD, the percentage of the population, rather the sample hanging outside of the central 3 votes, is increasing as PMV shifts away from 0. So, does it work? Does the comfort equation, does the PMV index, and does the PPD index actually work in practice? So, this is the work of thermal comfort field studies. And so, in the classic thermal comfort field study, we go into a building, a real building with real occupants. Here's an example of a modern Australian office building, circa 1905. And we administer a very simple thermal sensation scale to our occupants. And at the same time as they're doing their thermal sensation ratings, we're doing a slew of environmental measurements with instrumentation such as you see in this slide here. And the key point here is that we're measuring all of the basic input parameters for the PMV, PPD calculations. And we're also registering some checklists of Clow values and metabolic rates. And this classic field study approach has been applied in many, many different locations, many, many different buildings around the world. Back in the 90s, I was tasked with a colleague of mine, Gail Brager from Berkeley, to pull together these field studies and into a consolidated thermal comfort database, and to test whether the PMV, PPD indices are actually matching up with what we were observing in actual buildings. And the upshot of that analysis was that, that yes, they were actually, in air-conditioned, centrally controlled buildings, they were doing pretty well. The indices were quite successful, and it suggests to us that in some ways, the occupants of air-conditioned buildings were adapting to what air conditioning engineers were providing them. And so if the PMV equation says a comfort temperature should be 22 degrees, we supply 22 degrees, and people will adapt to what we give them. And the primary means of adaptation, of course, clothing would be the obvious one that many of us have chosen this morning. Putting on a jacket because our coils are too big in this auditorium. So in terms of predicting the comfort temperature, the PMV PPD model does a reasonably good job. But what about the question of variability and predicted percentage dissatisfied? It's in some ways it is the key question of this presentation. So if we look in the standards, we see that buildings can be classified as Class A, Class B, or Class C, depending on how tightly they control around a temperature corresponding to PMV 0. So PMV plus or minus a degree, PMV 0 plus or minus a degree Kelvin is predicted, according to the PPD equation, to have a dissatisfaction level of 6%. It's about as low as you can get. Widening the temperature band out to 4 degrees, the dead band out to 4 degrees around 0, we expect a PPD of 10% or better. And widening the temperature dead band even further, plus or minus 3 degrees, we would expect the PPD to go up to about 15%. So how does that stack up in the field studies? Well, ASHRAE commissioned some very detailed field studies back in the 90s in which we measured all of those parameters. I showed you a slide of basically how they worked. And what we've got here are four field studies from Australia, 4 that I was involved with, and very large surveys. We're talking about thousands of respondents in these field campaigns. And when we analyse the data collected in those field campaigns and, if you like, filter out just those observations that complied with the Class A prescriptions and the Class B prescriptions and the Class C prescriptions, we should theoretically see that PPD, predicted percentage dissatisfied, increases as we go from Class A to Class B to Class C. So here we've got some studies from a hot, humid climate zone in the north of Australia, and as we descend from Class A temperature prescriptions down to Class C, there's no discernible impact on the levels of acceptability. The PPD stays pretty constant. I shouldn't say PPD, I should say the observed percentage dissatisfied stays pretty constant from Class A to Class C. And that pattern is repeated in pretty well all of these surveys. 77, 77, 84, 86, 84, 84. Generally speaking, around about 80% acceptability. Doesn't seem to budge, regardless of how tightly we're controlling the environmental conditions. So when I've presented that slide at other conferences, it's been pointed out by some of my colleagues in the thermal comfort community that I've ignored the local discomforts. Everything about that previous slide was really just about the global PMV scores of those buildings. But there's a slew of local discomforts that are written up into the standard, and they include draft or unwanted local cooling because of air motion, vertical temperature gradients through the occupied zone, cool or warm floors, probably not that relevant in office studies like the ones that I was just describing, and then radiant asymmetry, hot surfaces in the environment, such as glazing that is being irradiated by direct solar gain. So in the ISO standard 7730, there are predicted percentage dissatisfaction equations for each of those 4 local discomforts. And so what I've done is I've gone back to the 4 field studies that I was just talking about and further filtered so that we extract those observations that don't comply with the global or the local dissatisfaction criteria of Class A and Class B and Class C buildings. And the upshot is this, that again, it doesn't really have a discernible impact on acceptability levels as we go from Class A to Class C. In Townsville, in a hot, humid climate zone, it's around about 81 to 78%. In a hot, dry climate zone, it actually is very low, but that's because the sample size complying with all of the very stringent requirements for Class A, it drops down dramatically. We only had 12 observations that satisfied those criteria. But up here in Class C, we had 380 observations that met the full requirements. That's global and local. And acceptability level was at 87%. So the point I hope to make here is that tight temperature control doesn't seem to have a discernible impact on acceptability inside these buildings. So why doesn't thermal acceptability improve in buildings with tighter temperature controls? Well, I've mentioned it already, but the adaptive principle would seem to be a fairly logical explanation going on here. If there is something in the environment that causes discomfort, people will do something about it. They will act or behave in a way that will restore their thermal comfort. And as Professor Zhu discussed in her presentation, there are layers of adaptation that we can refer to in this context. Probably the one that's most relevant, I think, to this discussion would be the psychological, which is about the expectations that people bring to their buildings, what they expect. If they expect an invariant indoor environment, they are probably hypersensitive to variation, but if the variations are wider and they're used to those variations and have the opportunity to adapt to them, well then their tolerance of variations will increase. So the bottom line here is that there are no absolutes, which is kind of disappointing from the point of view of somebody who spent 30 years basically developing thermal comfort work, and to come to this conclusion that there are no absolutes in thermal comfort, that everything is relative, is stands in contrast, if you like, to the deterministic analytical approach that I was describing earlier in the PMV and PPD. So perhaps thermal variance and local discomfort could actually be a positive attribute in the thermal environment. And rather than defining comfort in a subtractive way, as the absence of thermal sensation, perhaps as an alternative. And here we can refer to the alliesthesia concept, which I'll describe for you just briefly. Alliesthesia is introducing, if you like, a new lexicon or a new language of thermal comfort, where we talk about thermal texture, the variations in the thermal environment. And in the last couple of days since arriving in Hong Kong, I've certainly experienced some very rich thermal texture. No problems there whatsoever. As we're going in and out of buildings, short exposures in 22 degrees and then short exposures in 32 degrees with elevated humidities. And all the while, my thermal sensations are using the full scale of that 7-point scale, using the full range of opportunities. Now, thermal alliesthesia is about that process where we have contrasts, both through time and also through space, variations in the thermal environment. And I use this term thermal polarity to differentiate those combinations of conditions that are associated with discomfort from those that are associated with pleasure. I'll elaborate that in the next slide. So it leads me to propose an alliesthesial principle, which is kind of in some ways the hedonic flip side of the adaptive principle. And that is that if options are available, neutral occupants will actually deliberately exploit local adaptive opportunities to induce thermal pleasure. That thermal neutral is not necessarily the desirable endpoint of the thermal comfort game. So thermal alliesthesia goes back, as I said in my introductory remarks, to some physiological work that was done in the 1970s. And Kabanak is the name that was most closely associated with the concept. More recently, Professor Kuno in Japan has been using the similar concepts. And there are positive aspects of thermal alliesthesia and negative aspects. In positive contexts, it's about the internal state of the organism. If let's say we're feeling slightly warm, any cooling applied peripherally will be experienced not just as neutral, but rather as a thermal delight, as a thermal pleasure. Negative alliesthesia will be the flip side of that. If in let's say outdoor Hong Kong conditions at the moment, we're walking from a shaded position at elevated temperature and humidity into a direct sunlight, that additional heat load is getting the polarity of the alliesthesia wrong, and the result will be actually more discomfort.
5 minutes, Richard.
Okay. So I'm not going to have time to go through the experimental work that underlies some of this stuff on alliesthesia. Suffice to say that we're now we're exploring the range of alliesthesia from the zone immediately around the preferred temperature out to the more extreme conditions where perhaps approaching thermal stress. And a few basic points that I can make about that, or that series of studies, is that the magnitude of thermal alliesthesia, the magnitude of the pleasure, if you like, enlarges as we progress from the preferred temperature on outwards towards thermal stress. So it begs the question, can we have thermal alliesthesia, can we have thermal delight or thermal pleasure in conditions just around preferred temperature or just around neutral? Not necessarily right on neutral, but just in the zone that we can refer to, let's say, as the adaptive temperature range. And the answers are going to be elaborated in more detail in the next presentation, so I won't spend too much time on them here. Suffice to say that spatial differences of temperature across the surface of the body can indeed deliver thermal pleasure and thermal alliesthesia. I was going to show some finish, in some ways, on a classic study by Tanabe. I hope he's in the audience. Tanabe did some studies in his PhD back in the 1980s, published in the early 90s in ASHRAE, looking at the impacts of fluctuating air movement on thermal comfort. And large sample of human subjects, 64, 0.5 clo, 40 minutes exposure at 27 degrees Celsius, and then a variety of exposures with different patterns of air movement. I'm just going to look at two of them at the moment. The constant air movement with a constant airspeed of about 1 meter per second, and a sine wave with a period of 10 seconds, again with the mean speed of 1.0 meters per second. And we set up a skin model, a numerical skin model, to interpret the observations that Tanabe made in his experimental studies. And our skin model has thermoreceptors embedded at the depths prescribed by Hensel in the classic text on thermoreception. And the upshot of this analysis was that Tanabe's observation that the sine wave, the fluctuating airspeed, delivering more cooling or a subjective cooling effect than the constant airspeed, can be explained by the activities of the cutaneous thermoreceptors, in particular the cold receptors, that are particularly responsive to dynamics in skin temperature. So, a few basic conclusions here. The first is that no matter how precisely applied, the subtractive approach to thermal comfort, that is the removal of thermal sensation altogether, can achieve no better than about 80% thermal satisfaction. Or I shouldn't even say thermal satisfaction, I should say not dissatisfied. So perhaps it's time to eschew our notion of isothermal, homogeneous, steady state indoor climates and start designing thermal texture and thermal counterpoint as a source of thermal pleasure into our built environments. The concept of alliesthesia, and this is probably the most important point in my presentation, the concept of alliesthesia and within the adaptive comfort zone opens up lots of new interesting research possibilities, especially for the younger members of my audience this morning. So thank you very much.
Thank you, Richard, for this very well-balanced and structured presentation. It's really a pleasure.